Now that we know a Black-Scholes formula, and we know that it depends on the current spot price, the strike price, the risk-free rate of return, the continuous dividend given by the asset, then the volatility of the underlying asset, and the time to maturity of that particular asset. Now, given all these parameters can change over time, or with a small change in any of these parameters, I want to know how each of these parameters have an impact on the price of the call option or the price of the put option. What if the underlying spot price changes by 1 unit? What would be the impact on the price of the call option? Or if the strike price increases by 1 unit, what would be the impact on the price of the call option? What if the risk-free rate of return changes, let's say, from 6% to 6.5%? How is the option premium, whether it is call or put, how is the option premium getting impacted? And using the Black-Scholes formula, how can I compute the impact of change in price of derivative with respect to change in any one of the underlying parameters, the spot price or the strike price or the risk-free rate of return or the volatility. So these are what are typically called as the Greeks. So initially we have a few important Greeks like delta, which talks about the rate of change in the value of a call option or a put option with respect to the change in the underlying spot price. So this is what we are calling as delta. And there is one more element called gamma, which talks about the rate of change of delta with respect to the spot price change. Or the other way is rate of change of call price of the call option with the change in the spot price. Rate of change of the delta, which is again the rate of change of price of the call option with respect to change in the spot price. That's the reason we talk about it as a second partial derivative of the price of the call option with respect to the change in the spot price. Then we talk about theta, which a T here talks about the time, rate of change of the price of the call option with respect to the time. Then we are talking about a rho. Again, the first letter R talks about the risk-free rate of return. Rate of change of the price of the call option with respect to the risk-free rate of return. Then we are talking about Vega, again V, which is talking about rate of change of price of the call option with respect to volatility, so probably sigma or V. So though there are a few more, probably there is lambda, which talks about the rate of change with respect to the strike price. So there are a few more, but the most commonly used Greeks are typically around these, right? Either I can take the equation of the Black-Scholes, and based on that I should be able to find out what is the delta, what is the gamma, what is the rho, what is the vega of this particular call option, so that I can quickly get into the hedging decisions on a dynamic basis. So this can really help me in taking the hedging decisions, or probably the buy sell decision, to make my securities or the portfolio probably delta neutral, gamma neutral. We'll talk about the hedging process in the later session, but at least the understanding of these things, or computation of these things from my underlying Black-Scholes equation formula, will help me to see how is each of these parameters are coming up, and how do I typically use them for various hedging and decision taking purposes, right? So let's look at how we can try to derive the formulas from a typical Black-Scholes equation for understanding this. Okay, so first we know that the Black-Scholes formula for a call option, let me take it as e power minus q t minus t minus x e power minus r t minus t. This is the price of a call option. And now, if once I know the delta of a call, or once I know the Greek for a call, I can do the same for a put by using the call put parity relationship, or I can use a similar kind of a formula for put, and I can very well go ahead executing the formulas for the deltas for, or the Greeks for various put options as well. So let me start with delta. Delta, I know that it is the change in the price of the call option with respect to change in the spot price. So here I can very well differentiate this expression with respect to S. So it gives me e power, probably here I have nd1 and I have nd2 as well. Alright. So here it becomes e power minus q t minus t nd1. I am differentiating this, so probably you multiplication rule, taking this as one term and this as the other term. So this, and the derivative of s is 1 plus s times, right, or I can very well take out. So probably let me do something like this. The price of the call option is S e power minus q t minus t and d1 minus x e power minus r t minus t and d2. Now I am taking the derivative of c with respect to s. So probably in the first term, this contains s and even this contains s, whereas here only this contains s. So what I'll do is I'll take this common out, and when I'm doing a derivative here, it is coming out as nd1 times the derivative of s with respect to s is 1 plus s multiplied by n dash d1, right, where s multiplied by n dash d1, and I'm taking the derivative of d1 with s. So this is the first part. And what about the second part? This is constant. X with respect to s, it does not change. X e power minus r t minus t. So n d2, I'll take it as n dash d2, and I'm taking it dou d2 by dou s. right? So this is what is the initial expression, and what we can very well go ahead with is we will see that we will we will try to simplify this. So we'll try to simplify this. Now, first of all, we know that ND1, if I have to simplify this and get into a one interesting relationship, we know that ND1, I can write it as 1 by root 2 pi, going with a typical probability density function, or this is a cumulative distribution function, so I can write it as minus infinite to d1 e power minus x squared by 2 dx. But using differentiation and integration of the improper integrals, if I am taking the derivative of this one, I can very well write it as e power minus d1 squared by 2. Correct? 1 by root 2 pi e power minus d1 squared by 2, and probably n dash of d2 I can very well write it as 1 by root 2 pi e power minus d2 squared by 2. And we are also looking at, now if I want s time s e power minus q t minus t n dash of d1, if I want s e power minus q t minus t, I want let's say n dash of d1. N dash of d1, anyhow we have found this out, we'll come back to it. Now I'll try to find out the value of s e power minus q t minus t. So here what I am trying to write is, I will try to write this as k by s into s, k by s, sorry, k into s by k. So this is still s. So s I will write it as k into s by k, and probably I'll try to write it as this part I'll write it as e power minus r t minus t into e power r minus q into t minus t. This I can write it. So at the end it is becoming s e power minus q t minus t only. So I will segregate the terms, k e power minus r t minus t into s by k e power r minus q into t minus t. Fair enough? So this I will write it, this part I will leave it as it is, k e power minus r t minus t, but this I can write it as e to the power of log s by k, because this is nothing but s by k, because x is nothing but e power log x. So using that, here I will write it as e power log s by k, and this I will write it as e power r minus q into t minus t. So overall it is coming out as k e power minus r t minus t, and this is coming out e power log s by x instead of k. K and x somehow I am using interchangeably, so probably let me take it s by k plus r minus q into t minus t. This is what is coming in the numerator. And now if I go ahead, d1 equal to, when I look at d1, we talked about log s by k plus r minus q plus sigma squared r minus q plus sigma squared by 2 into t minus t by sigma root t. So from here probably I am trying to split it. d1 is log s by k plus I can write it as r minus q into t minus t by sigma root t plus I can write, so here probably if I go back, probably let me remember this step here, and I'm using d1 is log s by k plus r minus q into t minus t by sigma root t minus t, and I'm segregating the other part, which will give me sigma root t minus t by 2. This is what is coming out as d1. So because of that, what I can very well write, earlier we have come out log s by k when I have to find out s e power minus q t minus t. It said it has worked out to log s by k plus r minus q times t minus t. So this can be very well written as d1 minus sigma root t minus t by 2, right, if I'm taking it to the other side, and probably this entire thing is getting multiplied by sigma root t minus t. So overall it is coming out as d1 sigma root t minus t minus sigma squared by 2 root t minus t, right? And this is the value coming out for s e power minus q t minus t. Now what I want to do is I want to multiply this side with e power minus d1 squared by 2. Let's say I'm multiplying this side with e power minus d1 squared by 2. So this also probably, okay, here we had something earlier extra, k e power minus r t minus t into e to the power of this one. This is what we had. So now when I am bringing in some additional term on the left hand side, I have to multiply it with e power minus r. This side also I have to multiply with e power minus d1 squared by 2. So overall working out to e plus sigma d1 sigma root t minus t minus sigma squared by 2 root t minus t. So overall it is working out as k e power minus r t minus t, and this is working out as e power minus of, if I am looking at d1 minus sigma root t minus t whole squared by 2. This is what is coming out here. So which is nothing but probably I can write it as k e power minus r t minus t e power minus d2 squared by 2. So overall it is coming out that s into e power minus q t minus t d1 e power minus d1 squared by 2 is equal to k e power minus r t minus t e power minus d2 squared by 2. So probably this part is coming out as s e power minus q t minus t n dash of d1 is equal to k e power minus r t minus t n dash of d2. This is a very important expression for valuing majority of the Greek. So wherever I am getting s e power minus q t minus t n dash of d1, I can very well substitute it with k e power minus r t minus t n dash of d2. So this is a very important expression, right, which will help us in solving a number of Greeks. So probably one easier point for us to remember, probably it's very much essential to remember this formula, S e power minus q n dash of d1, the derivative of d1 is same as k e power minus rt n dash of d2. Right, so that can directly be taken up, and so from that perspective, now let's go back finding out the delta dou c by dou s. Now we can easily make out what is the dou c by dou s. Now I will take e power minus q t minus t, if I take out n d1 plus s times n dash d1 times dou d1 by dou s minus k e power minus r t minus t n dash d2 dou d2 by dou s. Now this is where s, so probably k e power minus r t n dash d2, in this entire place I can substitute this. So it's coming out like n of d1 e power minus q t minus t plus s e power minus q t minus t n dash d1 dou d1 by dou s minus, instead of this entire thing I will write s e power minus q t minus t n dash d1 dou d2 by dou s. So what is happening out is it is coming out as n d1 e power minus q t minus t. I'm simply taking this entire thing out, s e power minus q t minus t n dash d1, and it is simply coming out as dou d1 by dou s minus dou d2 by dou s. Now d1 by, so when I'm looking at now d1 log s by k plus, right, r minus q plus sigma squared by 2 into t minus t divided by sigma root t minus t. Now this part does not contain any s, so I'm not bothered, this is a constant, whereas this part I can integrate it. So this also I'll write it as log s minus log k. So even log k part does not contain any s. So probably the derivative is coming out as 1 by sigma root t minus t, and log s derivative is 1 by s. So whether I am going for dou d1 by dou s, it is coming out as 1 by s sigma root t minus t, as well as dou d2 by dou s is also coming out as 1 by s sigma root t minus t. So because both of them are same, this subtraction is becoming 0. So this entire multiplication is becoming 0. So from here it is coming out that the delta of the call option is nothing but nd1 multiplied by e power minus q t minus t. So this is what is the formula associated with the delta of the call option. And the same logic goes again. If I want, now I know that the delta of the call option is nd1 times e power minus q t minus t. I can very well find out the gamma. So gamma is nothing but the dou delta by dou s. So here if I am taking the delta of this, yes, this part is nothing impacted by S. So n d1 going as n dash d1 and dou d1 by dou S. And what is n dash d1? We have already seen earlier. The n dash d1 is e power minus d1 squared by 2, 1 by root 2 pi, and dou d1 by dou S, we have already found out that it is 1 by S sigma root t minus t. So this is how I am able to compute. So e power minus q t minus t divided by S sigma root t minus t 1 by root 2 pi e power minus d1 squared by 2. So this is what is coming out as the delta gamma of the call option. We can directly find out using the relevant expressions. We can find out the gamma associated with each of the security, each of the options, right? Once I know that this is my delta, I can very well find out my gamma by differentiating the delta with respect to S. So that's one way we can find out our gamma of the call option. Then we'll also look out for finding out the vega, the theta, and the rho. All right. In all these things, the important thing is to remember that one equality relationship. Again repeating, S e power minus q t minus t n dash d1 is equal to x e power minus r t minus t n dash d2. This relationship x or k, probably I have been using them interchangeably, both of them mean the strike price itself. Now let's say I want to find out the vega, the change in the call option with respect to the sigma. So here we say call option price S e per minus q t minus t nd1 minus x e power minus r t minus t nd2. So when I want dou c by dou sigma, in this entire thing does not contain a sigma, only this one contains. So probably I can very well write it as S e power minus q t minus t n dash of d1 and dou d1 by dou sigma minus, this is becoming x e power minus r t minus t n dash d2 dou d2 by dou sigma. Again, this entire thing I can very well represent this part. So which is S e power minus q t minus t n dash d1 into dou d1 by dou sigma minus dou d2 by dou sigma. This is what is typically coming up. Right, dou d1 by dou sigma and dou d2 by dou sigma. So basically we can very well write, see, we know that d2 is equal to d1 minus sigma root t minus t. So we can very well write it by take the partial derivative, dou d2 by dou sigma is equal to dou d1 by dou sigma minus root t minus t. So other way it is coming out as, probably if I have to evaluate it, dou d1 by dou sigma minus dou d2 by dou sigma is nothing but square root of t minus t. So overall it is coming out that the vega is nothing but S e power minus q t minus t n dash of d1 we have already seen 1 by root 2 pi e power minus d1 squared by 2, and this is coming out as root t minus t. So that is what is the way the vega of a call option can be worked out. And what we see is Vega is the same for a call option as well as a put option. Even the gamma is the same for a call option as well as a put option. Now, when I am looking for theta, probably the same things you can derive even for a put option as well. But all these calculations become more and more simplified, become more and more easier once we remember that equality which we have derived, s e power minus q t minus t and dash of d1 will be the same as x e power minus r t minus t and dash of d2. Correct? Now when I am looking at deriving the theta, so change in the price of the call option with respect to the time. The same logic goes through, right? I can very well go through the same logic as, so here when I am looking at with respect to t, there are so many things working out. When I am looking at deriving with respect to t, there are so many things because c is s e power minus q t minus t and d1 minus x e power minus r t minus t and d2. So if I have to differentiate with respect to t here, probably this is coming out for the t is present here as well as here. So the first term comes out, let's say s e power minus q t minus t and dash of d1 and dou d1 by dou t plus s and d1. If I have to differentiate it with respect to t, it is coming out as e power minus q t minus t, and a derivative of this is coming out as q. Similarly, the right hand side minus, again t is present here as well as here. So it is going to become minus x e power minus r t minus t and dash of d2 dou d2 by dou t minus x and d2 e power minus r t minus t into r. This is what is typically coming out. So probably at least these two I can join with the relationship. So I can very well write it as s e power minus q t minus t n dash d1, and this I can very well write it as dou d1 by t minus dou d2 by t. This part not an issue at all, dou d1 by t minus dou d2 by t, and we are having these two qs and d1 e power minus q t minus t minus rx and d2 e power minus r t minus t. And just to evaluate dou d1 by t minus dou d2 by t, we have already seen d2 equal to d1 minus sigma root t minus t. So what I can very well do is dou d2 by dou t equal to dou d1 by dou t minus sigma times the square root, the differentiation of this is 1 by 2 root t minus t and into minus 1. So it is very well working out as d1 by t minus dou d2 by t is nothing but minus sigma by 2 root t minus t. So obviously the whole formula is working out in a straightforward manner, which comes out as s e power minus q t minus t. I know n dash of d1 is 1 by root 2 pi e power minus d1 squared by 2 into minus sigma by 2 root t minus t plus this part qs nd1 e power minus qt minus t minus rx nd2 e power minus rt minus t. So that's the way we can very well derive the theta of a call option, and almost everything can very comfortably be derived once we are having this kind of orientation. The same logic we can use to derive the row of a call option as well. So all these derivations are giving us a clarity that once I have the underlying data with me, I can very well compute the once I have the 5 or 6 underlying data elements with me, I can very well compute the Greeks, which indicate the sensitivity of the call option prices with respect to the underlying variables, and based on that, if at all any kinds of risk is typically coming up, I can very well try to address those kind of risks quite comfortably. So understanding how these things are derived is very much important, under what conditions, under what assumptions these Greeks are working out, and at the same time feeding these formulas into a spreadsheet can really give us a good leverage in terms of quickly working out and seeing how the Greeks have been changing for different instances of different changes in the underlying variables. All right. So that's an important thing which I wanted to discuss as far as the Greeks are concerned. All right.